Welcome to the Artificial Intelligence Podcast with your host, Dr. Tony Huang. Today with a special guest, Jay. Can you introduce yourself?
Sure. My name is Jay. I'm the co-founder and CEO of Lemurian Labs. We're essentially rebuilding and rethinking AI infrastructure as a whole. Everything between PyTorch and TensorFlow and JAX and the hardware you're running on like GPUs, TPUs, Trainiums, Inferentias, CPUs. We're essentially consolidating all of that stack into one thing that is easier for developers to use and scale and debug.
Now, Jay, your background says that you're like a former AI advisor for NASA. Can you disclose any of the work that you've done with NASA?
Yeah, so when I was at a company called Geometric Energy, we had a lot of different contracts with a lot of different companies. One of them was NASA. And I got to work on the Mars rover program, helping with vision-based navigation, worked on flight dynamics and a lot of different things like how do you build grid pins to help optimize landing in certain places, if in different kinds of conditions and weather scenarios. In particular, I worked a lot with the Tier Development Lab, and it was essentially stood up to solve all the problems that conventional science could not in hopes that AI could help solve them. Right? So you're studying different kinds of planets and exosystems, looking at satellite data, and then how do you use computer vision methods or generative computer vision methods to upsample these images to study them, right? And then create topographical maps of, oh, this is a crater. This is what the depth might look like. There might be water here. So maybe you can reduce your search space and look for certain interesting things here and navigate the rovers to go explore. Or solar flares. What is the impact of solar flares and how far will they go and so things like that.
So, of your work with like NASA, what have you taken away that helped you like build like new software for the AI frontier?
Well, it was very different problems. So the problems in solutions space didn't fully transfer over, but I think it's more the approach to problem solving that has always been constant across all the different places I've worked, is I've always looked at problems that were that seemed further away, right, or harder to do with conventional tools. So you have to essentially rethink the constraints that are available to you and how do you bend them to some degree. What technological innovation allows you to change the constraints and solve this problem? And that's always the question that we ask whenever we're doing anything over here is what has to be true in order for this problem to be solvable? Or even if it is solvable, why can't we do it 10x better? Right? Again, in order to do 10x better, it has to go beyond what is currently possible, and you're forced to think about new technology. And usually the thing that we're going for is how do we make it 10x more efficient or cheaper? That is the more impactful technology.
So, like right now, the like AI computing, it like consumes a ton of electricity. Like online that says that like there's a recent study that said like it's going to consume 20% of the world's electricity by 2030. What type of like actionable steps should the industry prioritize to make like large scale AI sustainable, especially beyond the current incremental improvements?
Yeah, so I believe the study and a few figures that have been put out recently are 945 to 950 terawatt hours for AI electricity, which is about 2x what global demand is today by 2030. And the biggest driver for that is building more data centers for AI. It takes into account that models are going to be bigger and there'll be a proliferation of more models and more people will be using them. Now, a lot of these calculations take into account certain utilization rates for hardware. A lot of companies today, sadly, are operating in the 10 to 15% utilization on these very large clusters. Right? That should not be the case, but it tells you that something is broken. Because when the entire cloud computing paradigm was started, we lived in a 60, 70% utilization to in some cases up to 85% utilization. And that was part of the economic model. When we went towards AI, we only had one option for a vendor of GPUs, and everything was built around it, right? And the rate of change of models was such that it's very hard to get optimized all the time. There's very few people that know how to really get performance. And then you look at all the other systems that are available to you, it becomes really hard. And at some point, AI became less of a programming challenge and more of how do you program a supercomputer. And they're very different problems. When I started in AI, I could build a state-of-the-art model with 2 GPUs. Today, we're looking at 200,000 GPUs, and it's only been 12 years. So we're looking at a 5 order of magnitude increase in computer requirements inside of 12 years. That is insane by any measure. So when you're looking at model growth in that way, and the way software has to accommodate, how infrastructure has to change to accommodate that, and how hardware topologies and clusters are changing to allow for that kind of scaling, there's a lot of inefficiencies that come into place. Whenever you are scaling anything aggressively, you don't have time to optimize, right? And that is the world we found ourselves in. Now, there are a couple of other things that we need to consider. GPUs by default consume energy, and they are designed to consume a lot of energy. They don't care about latency, they care about throughput. So they want to be doing a lot of batch processing. So they're great for training for that reason. Less so for inference. They're starting to get better and they have been optimizing to get better. But the utilization is still going to be low. Models are becoming bigger and more dynamic. You have mixture of experts with different kinds of routing. You have reintroducing models with RL per chain of thought. You have agentic systems. And now you have multi-agent systems where multiple agents are coordinating with each other and reasoning and doing a lot of other things. All of this is going to further decrease utilization and increase overall compute costs. So today, every single company in the world is essentially subsidizing AI so that more people can use it, right? A lot of companies that I have seen are losing an order of magnitude per query that they're serving to a customer, right? So there's an appearance that token cost is falling, but the energy cost is the same. So something is amiss. Now, the things that they take into account is an estimation of the number of GPUs you will need in order to build this. There's not enough energy to actually supply a lot of them. Right? The biggest limiter in terms of building this out is not the number of GPUs you can tap from TSMC. It is actually there's not enough complex packaging parts or high bandwidth memory, and it's not electricity. So a lot of these models take into account theory, but they don't take into account the practicality of building this. I don't think we'll actually get there. The EU, for example, actually has a mandate to reduce overall energy consumption for a lot of advanced compute and data centers by about 11.7% by within the next 2 years. So they will actually slow things down. In terms of the US, in order to build out to get to that scale, we will need nuclear. We're not close. There's SMRs and things, but building multi-gigawatt data center campuses is non-trivial. It takes a very long time. So there are solutions in play. They will take longer to build than we think. And in terms of hardware, we have seen the end of Moore's law. That is going to change how hardware is built. It is going to err towards the side of more energy efficiency because transistors will not really get faster. So a lot of things will start settling themselves to some degree.
Yeah, I agree with some of those. I'd say like a big problem that the AI space has is that, for instance, generative AI is powered by transformers, and a transformer's like parameter has a quadratic relationship with the amount of VRAM on the GPU. So that means that like for small models, it requires a fairly large amount of VRAM, and then for very large models, it requires just a ton of VRAM. And so that right now we're kind of screwed because of like that transformer model, which got us up and running pretty quickly. There's been a lot of like research in trying to build a linear version of that transformer so that if it scales linearly, then we could use very large model on a lesser amount of VRAM, which allows us to not have to invest in such a large amount of our hardware. But also, I've noticed that a lot of data centers are popping up around the states with high frequency. But the problem that I've seen is that the people making those data centers don't know how to build it specifically for AI. So they don't have like water running to it to cool the hardware. They don't have like backup like power sources or generators in case like something goes awry with it. So these data centers pop up and they're not built for like generative AI like power. They're built as just like your run of the mill data center, which isn't correctly like in my opinion, I don't think they correctly built it. Like, what's your take on like my, what I've just said?
Okay, so training and inference fundamentally have different needs. So it depends on what you're building for, right? If you're designing a data center for training, you're essentially designing a warehouse scale supercomputer, and you want to be able to program this entire thing as one computer, right? That's where the warehouse scale computer kind of term comes from. If you're doing training, you're dominated not by the forward passes or by the massive reductions you have to do across the board for gradients. Like those will take 20 to 50% of overall time. And you're limited mostly by networking over there. So having a fat tree would be the ideal topology. And you want to have the maximum bandwidth possible. Right? So if you look at a lot of the clusters that people are building today, most people will go with a 400 gigabit Ethernet, right? But you want an 800 gigabit Ethernet instead. When it comes to inference, you care more about latency, so it does matter as well, but the topology of your clusters will again change. How much memory you have will change. What kind of chips you might choose will also change as a result of that. And you will be optimizing software differently for both of those environments as well, right? Because as your not just software doesn't change purely because of hardware, but also because of the topology of the system. So there's a lot of things to consider there. And you can't deviate too far because then your entire workload breaks and you have to go rewrite everything from scratch to get it to run. And you may end up with an entirely different model with different behaviors. So those are things you need to take into consideration when you're building two entirely different clusters as well.
Gotcha. So from like an industry's
Yeah.
perspective, what are like major bottlenecks preventing truly scalable AI systems? And then like how can like a software centric approach overcome that?
Your limit is always going to be software and bandwidth, right? Because you can't send things very far because signal does degrade and latency does matter in actual workloads. But to just go back to cooling and other things, it's not purely a data center problem or a data center builder problem. It's actually a systems problem from the chip builders up, right? Because the chip builders build their cards and their packages, and then they think about how do you spec out chassis with the system integrators. And if it's not designed for liquid cooling, it's going to be very hard for them to actually make that work. And very few of them are end up being percentage-wise being liquid cooled. And that's something that a lot of the hyperscalers actually work with the chip companies to spec out early ahead of time. Right? So some hyperscalers are actually part of the design process with some of the chip companies to make sure they get something very specific. Everybody else gets a step down. So there are a lot of things that are happening in the back end that do impact this. And liquid cooling is more advantageous for you're going to push the system really hard and it's going to get overclocked and you don't want your chip to melt. Right? So it's very great for that kind of high performance computing work. But in a lot of systems, you can get away with liquid, like air cooled. Like it will take you pretty far as long as you do it right. Now, as far as software goes, the entire programming model we've been dependent on for the past few decades has been one of writing kernels, right? A kernel is a very specific implementation of an operator that is specific to a hardware, right? Because you want to maximally leverage the resources this hardware has. But you make certain assumptions when it comes to doing that. You assume staticity of the environment, right? So you make assumptions about the availability of memory, what the clock speed is going to be. You benchmark things, you tune it, you do blocking, you do tiling, you do fusing, loop unrolling, and vectorization, and strip mining, and all the other fancy stuff. And then you start deploying it. And that's great, as long as you're programming a single GPU or a single CPU. But now imagine you're programming 100,000 GPUs, right? Will you still be writing and scheduling every single kernel individually? Because it doesn't really care about memory traffic, right? That is not the thing you optimize. When you go for large scale systems, you are communication bound and you're memory bound. You're not really compute bound. So you're optimizing the wrong thing. So what we essentially saw was there is this massive need for the ability to program large-scale heterogeneous computers. It could be at the edge where you have an SoC, and an SoC is multiple different parts. right? You have a CPU, a GPU, an NPU, some DSPs in the corners, and some other stuff. And you have to write things that are specific to each of those components. If you're programming a very large supercomputer, you need to manage networking, you need to manage memory for each of the CPUs and the GPUs, you need to program to each of them differently. There could be other things in that system like NICs. You could be thinking about GPU to GPU communication that needs to be explicitly managed. So today, if you're programming in the NVIDIA ecosystem, you're not just programming CUDA, you have the libraries on top. You're writing a lot of things in PyTorch. You have very specific graph APIs where you're saying you want to call into these custom kernels. You're doing PI for large communications. You have nickel. You have communications between NVLink. Then you have CPU to GPU transfers. All of those need to be managed, right? So it's a lot of things going on the developers need to go and wrangle to make work for that one system, right? And that is for that one workload. That needs to be redone to a large degree for any new workload if you want performance.
Now,
Well, that,
with the cost of AI compute like ballooning, like sometimes I'm seeing it compounded by hidden operational inefficiencies. What type of like industry level reforms are needed to advance or to like to make these advanced AI more accessible without these runaway spending?
software needs to change. The way you write software generally has to evolve with the times. The kernel-based programming model has came into light during the Cray era, and it's been several decades since. And it was great because CUDA happened as a result of that, and that allowed us to realize GPU programming, which got us here. But the problem has since changed. So instead of trying to optimize for compute, you need to start optimizing for data movement, right? Kernels actually don't matter in this world anymore, right? Because if you can't get data in and out of your system fast enough, there is no point in that kernel that you spend so much time on because you will never get that utilization. In fact, it is physically impossible to saturate an ALU, right? It's the math part of a chip. What you should be doing is writing from the point of view of your L1 and L2 to make sure those are as busy as possible so that data is resident where it's supposed to be in order for the maximum utilization to be realized. So that is what we started building. Is essentially a dynamic runtime that does all this fine-grained scheduling on device for you on the CPUs and GPUs at whatever scale, and we generate the kernels to best match the schedules. And we can adjust these dynamically as well in case you're hitting a GPU too hard, it starts overheating, and you're about to get thermally throttled. You don't want that to happen, right? Because then you're running an order of magnitude slower. And that cascades across the entire system. And small inefficiencies do cascade and multiply at scale. Right? So you want to avoid those and you want to have graceful degradation, you want to have checkpointing and restarting and all those things. And the right infrastructure can help capture a lot of this, right? Because it's very hard for developers to deal with this.
And then what are the most pressing challenges right now in facing, I don't know, like interoperability amongst like the AI tools, the frameworks, and the platforms that you're like seeing today?
Yeah, there is no interoperability, right? So every single vendor has its own stack, right? NVIDIA has CUDA, and that's all the library ecosystem on top. It's called CUDA-X. AMD has been trying to catch up. They built HIP and this entire ROCm platform as well, which is essentially, in some ways, a clone of CUDA. Intel tried to build one API originally, but then went towards SYCL. Other chip companies that are trying to build their own chips, be it Qualcomm or Cerebras or Samba Nova or Grok or Tenstorrent or all the others, are all building their own vendor-specific stacks. And a developer is never going to go and use those because they've already got so much written in CUDA. If you want to break out of that, you need to have something that is an order of magnitude better in terms of developer experience, right? If you're not getting all three of the P's, like productivity, performance, and product portability, no one's using it, right? And no one wants to sit around and learn a new way to write kernels for different kinds of hardware, right? Because that requires you having a pretty good understanding of the hardware itself, and being able to debug a compiler and do all the other things.
So like how could like open standards and like collaborative like ecosystems promote more transparent, equitable, rapid innovation in AI compared to like, these walled garden approaches from like the leading tech firms?
It's challenging. I haven't seen anybody really have a good answer to this anywhere, right? Open standards are great in terms of getting adoption, But then you very quickly devolve into a design by committee kind of phase because there's too many people that want different things and it gets pulled apart and things just stop making progress. We saw this with Intel. Intel tried to build one API as this uniform standard that everyone could use, but none of the chip companies wanted to be beholden to NVIDIA, to Intel. And they were like, we'd rather just have our own thing. And things stop progressing. And everyone else is like, I have a better standard, so I'm going to go build this. And all of a sudden, you have a dozen different standards, and nobody wants to use them. So people will just continue to use the thing they're most familiar with. And innovation moves much faster in closed ecosystems. So early days, you want to err towards an open ecosystem, sorry, to a closed ecosystem where you can make a lot of progress and get it to a good enough spot, and then you can open it. This is something we saw with PyTorch. Meta did an amazing job building PyTorch and getting a lot of developer adoption. They did it openly, but they ultimately had the final say. And then they moved it over to the Apache Foundation, where it was community kept.
Are there any additional like industry examples, perhaps like outside of AI, where open platforms decisively outperform closed systems that like you believe AI could should look for inspiration? My example would be like Airflow, Apache Airflow. Like everybody uses Apache Airflow now for pipeline. And there's companies like Astronomer, for instance, who's on the news recently this past week, which is why I said Airflow, but that took Airflow and commercialized it, and that's Airflow is like the leading open source platform.
Yeah, it's interesting. The database world has always been really good about this. If you look at Databricks, you look at Snowflake, you look at a lot of the other companies that are out there like Vast, they all built some commercial versions of open source databases. Linux is always a great example. Android is always a great example. But that's pretty much what they are. They're examples, right? Analogies are only as useful as far as they extend, right? And they throw away a lot of information to make things in the right make sense in a certain context. And it's something I've always struggled with is, good analogies, because you throw away so much information to make it fit. I feel like all the interesting stuff was in what you threw away. And I think AI is very different as an industry. And I think we may need to be revisiting some of the rule books about how we approach open source in this, because it is very easy to misuse. And because there's certain guidelines when it comes to a database, right? It's only going to use in a certain set of ways. With AI, it's so broad as a technology that you can do almost anything you want with it as long as it's been trained a certain way, that the controls around it are going to be fairly different. So yeah, the licensing is probably where a lot of nuance is going to be required.
Like final question, how can the AI industry collectively foster like a robust ecosystem that balances like innovation, accessibility, and accountability as systems become like further embedded in society?
It's hard to say a priori. I think we're going to get it wrong a lot. And we'll hopefully we have the right people who can learn and adjust and do the right things. But technology is not good or bad, right? It is a tool and it is an amplifier. And an amplifier can work in both directions, good and bad. So it comes down to the people who are building it. And how do we create the right incentives for them? Now, early on, when we think about radar technologies, it was a public-private government like collaboration to make this available for everybody, and that allowed a lot of innovations to happen later on. We may need something like that. I don't know if it's the right one, but it could be that. But yeah, I generally just believe that there's a lot of good people and they're building technologies because they want to make a positive impact in the world. And as technology becomes cheaper, more people have access to it, and the more people that have access to it, the better things get. Because as a single company building it, it is very hard to test all the different edge cases and use cases. So we should be trying to make technology as we should be trying to make GPT a general purpose technology.
Jade, thanks so much for being on the show. Do you have any like tips and tricks for AI professionals listening in that are trying to navigate the evolving landscape of AI hardware systems design and like industry alliances?
It's easier than you think. There's always things that are changing. Focus on the things that aren't changing because those will always be true, right? So every single neural network has an inductive bias, a prior, and then scaling usually takes care of a lot of things. As you are scaling, the other things matter less. So understand the interplay, understand what different kind of hardwares are good for at a high level, understand why you need a lot of memory for different kinds of things, understand what scale out looks like, and there's a lot of really good guides out there. Ultimately, don't feel like you need to be good at everything. Pick a certain direction and just work on that because you will always find more benefit from getting better at the thing you're already good at than you are picking up something entirely new.
Thanks so much for tuning in. And for the viewers at home, stay curious.